video, we are going to learn hybridization in molecules having lone pair of electrons. For example, ammonia and water. When you find out the hybridization of nitrogen in ammonia, first you have to draw the skeletal structure for ammonia. In ammonia, nitrogen is the central atom that is bonded with 3 hydrogens. Atomic number of nitrogen is 7, so the configuration will be 1s2, 2s2, 2p3. When you fill electrons in it, you will get 2 electrons in 2s and 3 electrons in 3p. For the formation of 3 sigma bonds with 3 hydrogens, nitrogen requires 3 half-filled atomic orbitals, and it already has 3 half-filled atomic orbitals. So when you hybridize them, you can't leave 2s alone. You have to include 2s when you hybridize the orbitals of 2p, and thus you will get 4 sp3 hybridized orbitals, in which one of the sp3 hybridized orbital contains lone pair of electrons. These 4 sp3 hybridized orbitals arrange themselves in tetrahedral geometry to minimize the repulsion between them. For the formation of 3 sigma bonds with 3 hydrogen, 3 of the sp3 hybridized orbital overlap with the 1s orbital of hydrogen and form sigma bond. So this sigma bond is formed by the overlapping of sp3 hybridized orbital of nitrogen and s orbital of hydrogen. Now come to the shape of ammonia molecule. As we have already discussed, for the sp3 hybridization, geometry should be tetrahedral and bond angle should be 109 degree 45 minutes. But in ammonia, one of the position of tetrahedron is occupied by the lone pair. And this lone pair repels bond pair according to valence shell electron pair repulsion theory. So these lone pairs repel bond pairs, and as a result of it, the bond angle reduces to 107 degree 28 minutes. But these lone pairs are not visible in the geometry. They are like ghost pair. They influence the geometry, but they are not visible in the geometry. That's why the shape of ammonia molecule looks like pyramidal. So the actual shape of ammonia molecule is pyramidal, while the geometry remains tetrahedral. Now come to the hybridization in water. So first of all, draw the skeletal structure of water. So here central atom is oxygen that is bonded with 2 hydrogens. Atomic number of oxygen is 8, so the configuration will be 1s2, 2s2, 2p4. When you fill electrons in it, you will get 2 electrons in 2s and 4 electrons in 2p. For the formation of 2 sigma bonds with 2 hydrogen, oxygen will require 2 half-filled atomic orbitals, and it already has. Now, when it undergo hybridization, it cannot leave 2s or one of the 2p orbital. So all these 4 atomic orbitals undergo hybridization and form 4 sp3 hybridized orbitals. These 4 sp3 hybridized orbitals arrange themselves in tetrahedral geometry to minimize the repulsion between them. Now for the formation of sigma bond with 2 hydrogen. 2 of the sp3 hybridized orbital of oxygen overlap with the 1s orbital of hydrogen and forms 2 sigma bond. Now come to the shape of the water molecule. As we have already discussed, for the sp3 hybridization, expected geometry is tetrahedral geometry with a bond angle 109 degree 45 minutes. But in case of water, 2 of the positions of tetrahedron are occupied by the lone pairs. And according to VSEPR theory, there is maximum repulsion between lone pair and minimum repulsion between bond pair and bond pair. That's why these lone pairs repel each other and also they repel other bond pairs. Due to this, bond angle reduces to 104 degree 45 minutes. And as we have already discussed, lone pairs are not visible in the geometry. So that's why shape of the water molecule looks like V shape or band shape. But the geometry remains tetrahedral.